everyone knows the name of the first of the planets in our solar system. Mercury was seen in ancient times and carries the name of a Roman god. We've known of its existence for thousands of years. It's not hidden in darkness, but thanks to its position next to the Sun, is bathed in brilliant light. And yet, it is the least explored terrestrial planet, having only been visited by 2 probes in all of our spacefaring history. Why is that? Is it boring? What do we truly know about Mercury? What are its characteristics and history? And how have we learned about it? I'm Alex McColgan and you're watching Astrum. And in watching this supercut, you're about to find out. Join with me as I teach you everything you might want to know about the first planet in our solar system, Mercury. When you think about the physical characteristics of Mercury, I'm sure you imagine it being the closest planet to the Sun, but also that it's this giant rock floating in space. You wouldn't be too far wrong with that, but it is much more interesting than what you may first think. For example, when I look at Mercury, I do think of our moon, but Mercury actually is visually more appealing than our moon. Look at it in its true color. The first thing that I notice is that it actually does have a color. It's not just different shades of grey. And what else? Well, did you know, for example, that Mercury consists of approximately 70% metallic and 30% silicate materials? So it's actually more metallic than rocky. Because of this, Mercury's density is the second highest in the solar system at 5.427 grams per centimeter cubed, only slightly less than the planet with the greatest density, that of Earth, at 5.515 grams per centimeter cubed. If Mercury happened to be the same size as Earth, that would mean it would pretty much have the same gravitational pull at its surface. But being the size that it is, its surface gravity is only 3.7 meters per second squared. If you were to compare its gravity to Earth, it would look something like this. This means the surface gravity of Mercury is only slightly less than what it is on Mars, and considering that Mars is a much bigger planet, that just says something about the density of Mercury. But before we leave the subject of Mercury's size, I want to show you one last comparison, that of Ganymede and Titan against Mercury. Now, Ganymede is the solar system's biggest moon and also the biggest moon of Jupiter, while Titan is Saturn's biggest moon and the second biggest moon in the solar system. These 2 giant moons are bigger than Mercury, as you can see here, but their masses are far less. If you look closely at Mercury's surface, you'll see its appearance is similar to that of our moon. It shows extensive mare-like plains and heavy cratering, indicating that it has been geologically inactive for billions of years. But it obviously was geologically active at one point, because one of the distinctive features of Mercury's surface is the presence of many narrow ridges extending up to several hundred kilometers in length. We'll talk more about these later. One of the most distinctive things you'll notice about Mercury is this huge crater on its surface called Caloris Basin, with a diameter of 1,550 kilometers. The impact that created Caloris Basin was so powerful, it caused lava eruptions and left a concentric ring over 2 kilometers tall surrounding the impact crater. At the antipode of Caloris Basin is a large region of unusually hilly terrain known as the Weird Terrain. If you compare this region to the rest of Mercury, you can see why it would have this name. So, what's it like on the surface of Mercury? Well, to start with, the surface temperature is hugely different all over. It can range from minus 173 degrees Celsius to over 400 degrees Celsius. It never rises above minus 93 degrees at the poles though, because there's no atmosphere retaining the heat. This means that there's quite a big difference between the equator and the poles, but this variation is also due to its orbit and rotation, which we will get back to later. The subsolar point reaches about 400 degrees, while on the dark side of the planet the temperatures are, on average, minus 163 degrees Celsius. Because Mercury is too small and hot for its gravity to retain any significant atmosphere over long periods of time, it's not able to retain any of the heat it gets from being so close to the Sun, which is why the dark side of the planet is so much colder than the side facing the Sun. Mercury, however, does have an exosphere, which is like an extremely thin atmospheric-like volume surrounding the planet. Molecules in an exosphere are gravitationally bound to a planet, but the density is so low that it can't behave like a gas because the molecules don't collide with each other. In this picture, you can see the MESSENGER probe's view of Mercury's exosphere. When solar wind hits the planet, it rips off certain atoms out of the exosphere, and what's left is this trail of atoms going into space. We call this the planet's tail, and every planet has this to a certain extent. Earth even does have an exosphere, but it starts at 600 kilometers above the surface. It's really the point where space and the atmosphere meet. Now, in the case of Mercury, this exosphere is not at all stable. Atoms are continuously lost and replenished from a variety of sources, which we'll discuss in more detail later. NASA has been able to confirm that craters at the North Pole of Mercury contain water ice. Mercury also has something which Mars lacks, an actual magnetosphere, or a magnetic field all around the planet. It is only about 1.1% as strong as Earth's, but it's still strong enough to deflect a lot of the solar wind around the planet. Mercury has the most eccentric orbit of all the planets, with a distance from the Sun ranging from 46 million kilometers to 70 million kilometers. Now, this is something a bit hard to imagine, but bear with me. Mercury takes about 88 Earth days to complete an orbit around the Sun. It also has a 3-2 spin-orbit resonance of the planet's rotation around its axis. This means it spins 3 times around its axis for every 2 times that it orbits around the Sun. It takes about 59 Earth days for Mercury to rotate on its axis once, which is what we call a sidereal day. By pure coincidence, this is almost exactly half its synodic period in respect to Earth, which is 116 days. So, between conjunctions of Earth and Mercury, Mercury rotates on its axis exactly twice. Historically, there was a big problem with that. Because of this coincidence, we believed that Mercury was tidally locked to the Sun for the longest time. You see, Mercury orbits closely around the Sun, meaning it was always tricky for astronomers to get a good look at it for most of its year. When it finally got in a good viewing angle from our perspective, we'd have a look at the face of the planet. 118 days later, we'd have another look during this prime observation alignment, and see the same face again. So to them, it showed that Mercury was tidally locked to the Sun. What astronomers didn't realize is that Mercury had rotated exactly twice on its axis during this time. It wasn't until radar observations of the planet that we found out that it does rotate slightly faster than it orbits. This 3-2 orbital resonance means that if you were actually standing on Mercury, it would appear that one day, from sunrise to sunrise, or what is called a solar day, is 2 Mercurian years. Standing on Mercury, that would look something like this. You would see the Sun rise relatively fast, and then as it approaches midday, it slows down and even starts going backwards before continuing on again to sunset. As you can see, that took a whole year, which means a nighttime on Mercury also takes a year. The Sun starts going backwards in the sky because approximately 4 Earth days before perihelion, the speed in which Mercury travels along its orbit equals the speed in which it's rotating. At this point, the Sun's apparent motion stays stationary. At perihelion itself, Mercury's orbital speed exceeds its rotational speed. So to a person actually standing on Mercury, the Sun appears to move backwards. 4 days after perihelion, the Sun's normal motion resumes. You can see this even clearer from a top-down perspective of Mercury. Twice a day on one of its poles, the Sun seems to pause and then continue on again. Something else to notice about Mercury's orbit is that it's inclined by 7 degrees to the plane of Earth's orbit. As a result of this, we can only see Mercury transit in front of the Sun when it's directly between us on Earth and the Sun itself. And because its orbit is inclined by 7 degrees, this only happens about once every 7 Earth years. The last thing we'll discuss about the rotation of Mercury is that its axial tilt is almost zero, with the best measured value as low as 0.027 degrees. This is even smaller than that of Jupiter, which has been measured at 3.1 degrees. And finally, do you want to see Earth from Mercury? Well, here we are, just a couple of pixels across. This photo was taken from the Messenger probe several years ago, and barring the newborns, every single one of us was in this picture. But what was Messenger, and why was it important? Well, let's start with a little context. When mankind first started sending spacecraft out to explore the solar system, the first planet to be visited was Venus, our closest neighbor, in 1962. Next was Mars in 1965, and then Jupiter in 1973. Only then came Mercury in 1974, and already this order might seem a little odd. The closest distance between Earth and Mercury is 77 million kilometers. In fact, it is the closest planet to us on average. The closest distance between Earth and Jupiter is 588 million kilometers, almost 8 times that. And Jupiter was visited again in 1974, twice in 1979, in 1992, in 1995, in 2000, in 2007. Multiple missions were launched to Saturn, Uranus, Neptune, to comets and asteroids, while Mercury got nothing for 30 years. Is this because it was deemed uninteresting? Did we discover everything there was to discover about it with that single first mission? No. The first mission was a flyby and only mapped about 40 to 45% of Mercury's surface. Actually, the real reason is that Mercury is one of the most challenging planets to visit in our entire solar system. Why? Well, as previously mentioned, Mercury exists in a furnace. Due to its proximity to the Sun, its surface temperature reaches highs of 430 degrees Celsius, so any probe visiting it would need to be highly heat resistant. But that same proximity to the Sun means that any probe launched towards it will accelerate faster and faster due to the immense gravitational pull from our star. Using rocket fuel against that would be like swimming up whitewater rapids. Combating the Sun's gravity required too much fuel for a Discovery-class spacecraft to carry. Slowing down the spacecraft enough to be caught up in Mercury's orbit seemed impossible. It was a question of weight. Weight is a challenging limitation when it comes to spacecraft. The heavier a craft, the larger a rocket needed to get it out of Earth's orbit, and the more expensive everything becomes. Scientists try to keep everything as light as possible to reduce this cost. As fuel takes up precious weight allocations that could go towards scientific instruments, scientists try to only take what is necessary to help them complete their journey. However, for about 30 years, scientists could think of no way to put enough fuel on a probe to get it to slow down enough to enter Mercury's orbit, especially if they wanted scientific equipment on board too. So, after the success of Mariner 10's flyby missions of Mercury in 1974 to 1975, Mercury exploration was put on hold. But in 1985, an orbital mechanics expert named Chen Wanyan realized that there was a way of getting a probe into orbit around Mercury that didn't need new technology. Instead, she had worked out a particular route an orbiter could take around the solar system that would slow it down enough to enter Mercury's orbit with only a few course corrections. Rather than going straight to Mercury, the orbiter would need to go a longer way. How long? Under Chen Wanyan's model, a craft would orbit the Sun about 15 times, flying past the Earth once, Venus twice, and Mercury 3 times before finally slowing down enough to enter its orbit on the 4th pass. All these planetary flybys would be essential. By skimming the planet's atmospheres, vital speed could be shaved off from atmospheric drag and due to the gravity of the planets. The entire route would cover a mammoth 7.9 billion kilometers and would take 6.5 years. Chen Wanyan's findings were not immediately picked up, but in 1998 NASA began to take an interest in the idea, and after seeing the feasibility of the route, they launched the Messenger probe in 2004. Messenger, or the Mercury Surface, Space Environment, Geochemistry and Ranging Probe, was only about 1.8 meters long and 1.3 meters wide, and weighed 1,100 kilograms. This is small and light for a typical NASA mission. Just a comparison, Juno is 20 meters long. Messenger came equipped with a powerful thruster, a ceramic heat shield to protect it from the sun, 2 solar panels, and a whole suite of scientific equipment for imaging and measuring data from Mercury. Scientists hoped to take advantage of this opportunity to learn as much as they could about the chemical composition of Mercury's surface, its geological history, its magnetic field, and its core, among other things. Messenger spent its first year in space making one orbit around the Sun before meeting back up again with Earth. This gave scientists a chance to test its equipment on a known astronomical body, to make sure there weren't any errors and to make any adjustments as needed. Messenger took some photos of Earth and the Moon, and also tested its other equipment to take readings of our atmosphere and magnetosphere. Fortunately, everything was working perfectly. As it began to head further sunward, Messenger employed a clever technique to help reduce its acceleration towards the Sun. It used its solar panels to catch solar radiation, like sails on a ship might catch wind. Solar radiation hitting an object actually pushes it very slightly, while this force is very tiny. Because Messenger's journey was so long, it really added up. Making the most of this phenomenon was one of the ways Messenger saved propellant and decelerated naturally. The next notable landmark in Messenger's journey came in 2006, when it did its first flyby of Venus. Sadly for scientists, this moment came at a time when Venus was exactly on the opposite side of the Sun from Earth, which meant Messenger was not in radio contact. It did take some photos of the planet which it later sent, but otherwise it performed no science. However, in 2007, it passed Venus again. At that time, another spacecraft was orbiting Venus, ESA's Venus Express. Messenger and the Venus Express took the opportunity to work together, performing the first ever simultaneous measurements of particle and field characteristics of the planet. But then it was on to the main event, Mercury. Messenger made its first flyby of Mercury on the 14th of January 2008, with everything going smoothly. The same was true of the second flyby. But during the third flyby in 2009, something went wrong. Messenger went into safe mode, which was designed to protect systems on the craft in the event of an error. How disappointing to have come so far, only for the mission to potentially fail during one of the final stages. Messenger remained in safe mode for what must have been 7 hours of stress for all the scientists involved. You see, Messenger had to pass through Mercury's shadow during this flyby, meaning it had to rely on its batteries for 18 minutes. Something wasn't configured right in the power management part of the software. Fortunately, Messenger's computer reset once power from the panels charged the battery, and it was able to continue with its mission, swinging around the Sun one more time before finally entering orbit around Mercury on the 11th of March 2011. Messenger took up an elliptical orbit around Mercury, alternating between as close as 200 kilometers and as far away as 15,000 kilometers. This is because Mercury acts sort of like a giant sun mirror, radiating heat back into space. Remaining too close to Mercury was too hot for Messenger, even with its heat shield, which was more designed to protect it from the Sun, 7 times brighter by Mercury than it is on Earth. So moving further away every 12 hours gave it a chance to cool off. Messenger spent the next 4 years in Mercury's orbit, far exceeding scientists' hopes and expectations for the mission, as they had originally planned for it to only last 1 year. Before launch, scientists had hoped that Messenger would take at least 1,000 photos over the course of its lifetime. However, Messenger took over 200,000 photographs, giving us a complete map of Mercury's surface in high resolution and color, as well as photographing nearby comets and other planets. On the 25th of December 2014, Messenger's propellant, so carefully saved up until that point, was finally about to run out. By this point, Messenger was orbiting a mere 25 kilometers from the surface of the planet. Scientists gave the thrusters one last burst to extend its orbit for as long as possible, but on the 30th of April 2015, Messenger crashed into the surface of Mercury. After a journey that had lasted over a decade and had covered literally billions of kilometers, Messenger's journey had come to an end. Messenger gave us a wealth of insights into Mercury before it died. On board Messenger were a host of scientific instruments, including a magnetometer to map out Mercury's magnetic field, which is thought to be generated by a dynamo effect in its molten core. Our fast rotation and tidal stretching from our moon keeps our core molten. But Mercury doesn't have a moon or a fast rotation. What it does have, however, is an eccentric orbit, more so than any other planet. Gravitational strength increases and decreases as it gets closer and further away from the Sun, so the tidal forces pull and squeeze on the planet, the friction of which keeps Mercury's core hot and the dynamo going. Unlike Earth's, it is offset from the center by about 20% of the planet's radius, and we don't really know why. Its magnetic field is only about 1% as strong as Earth's, but this still has an impact on deflecting a lot of the solar wind around the planet. However, due to it being closer to the Sun, the solar wind pressure is a lot greater here than it is around Earth. Add a weak magnetic field to the mix, and the magnetosphere around Mercury is compressed closely to the planet's surface. Earth's, on the other hand, extends many times the diameter of the planet away from the surface. Interestingly, these factors make the magnetosphere of Mercury highly dynamic. What does that entail? Well, for one, reconnection events are 100 times more common around Mercury than around Earth. Reconnection events occur when magnetic field lines snap together as the charged solar wind pushes against the planet's magnetosphere. When this happens, it allows a few of these charged particles to break into the planet's magnetosphere, entering a region of plasma in the planet's magnetotail. The flows you see in this simulation in the plasma region are from reconnection events. Another feature of the magnetosphere that Messenger detected was energetic bursts of electrons, producing hundreds of thousands of electron volts of energy. As Messenger orbited Mercury, it picked up thousands of these events, and mysteriously, they were mainly localized in the northern hemisphere, and were compressed towards the planet along the sun-facing side. This is still an ongoing field of study. However, scientists believe these electrons have been accelerated through breakdowns in the magnetotail, and they follow the direction of the magnetic field around from the South Pole to the north. Messenger also hosted a wide array of spectrometers. Spectrometers are important for detecting the composition of mineral deposits on the surface without actually having to take a sample. Spectrometers can also be used to detect the particles in the atmosphere. Now, Mercury doesn't have an atmosphere per se, but as previously mentioned, it has an exosphere, or an extremely tenuous atmosphere. It is so thin that the particles within it don't interact with each other. But what Messenger found out about this exosphere's relationship to the surface really surprised scientists. Mercury is covered with volatile substances. It isn't just a fried, rocky planet. It seems to be covered in potassium, magnesium, sulfur, sodium, and chlorine at a higher level than any other terrestrial planet, and much higher than on our moon. The fact that its volatile ratios have more in common with Mars than with Earth and Venus have completely disproved a lot of solar system formation theories that existed before Messenger arrived at Mercury. These volatiles are blasted by radiation from the Sun, more so at the equator than near the poles, which may explain why on the surface, some substances like potassium are more abundant in the northern hemisphere than around the equator. It is much hotter on Mercury around the equator than the poles, so the potassium there would have been heated enough that much of it has been lost from the surface to the exosphere. Now, the exosphere contains a lot of the particles you would also find on the surface, like sodium, potassium, and the others I mentioned. This exosphere is not at all stable. Solar wind picks up and carries away a lot of charged particles, and solar light pressure also pushes a lot of the neutral particles away. Were it not for the processes that replenish the exosphere, Mercury would lose it all to space over a relatively short time frame. While most substances certainly do come from the planet's surface, it also contains other elements like hydrogen and helium, which cannot be found there. So where did they come from? Well, as you may know, the Sun is made predominantly of hydrogen and helium, and interestingly, the solar wind carries these particles to Mercury. Some of the solar wind actually gets caught up in the exosphere and stays for a while. As far as we know, this is the only major source of hydrogen and helium in the exosphere. In these images, we see calcium, an unknown process of which means it's much more prevalent in the exosphere during the planet's dawn than dusk, and magnesium streaming away from the night side of the planet. In fact, Mercury's tail has been known about for a while. In these images, sodium ions are lit up as they stream away from the planet, making Mercury look like a comet. Incredibly, if you were to look up into the night sky on Mercury, you would actually see a faint yellow glow, reminiscent of city lights on Earth. This tail is seasonal. The eccentric orbit of Mercury means that its distance to the Sun varies throughout its year, and as it orbits, its orbital speed also changes. So, the time of greatest sodium emission is actually when Mercury is at its middle distance from the Sun. There was one other curious substance found in Mercury's exosphere that scientists really weren't expecting: water vapor. This could come from cometary tails as they pass by, or it could come from the ice deposits MESSENGER detected around the planet's poles. Surprisingly, water ice can exist on this scorched planet, but only at the bottom of permanently shadowed craters, forever protected from directly interacting with the Sun's light rays. The Earth-based Arecibo radio telescope had already detected highly reflective regions around the poles, and as images from MESSENGER came in, these regions matched up with regions of permanent shadow at the bottom of large craters. Estimates put the amount of water ice found on Mercury at 250,000,000 kilograms. This isn't huge by Earth standards, but it would be a significant boost to any future colony there to have that much water accessible. There were some other surprising features found on Mercury's surface too. Hollows were found dispersed all over. This is a unique feature to Mercury. While we aren't completely sure what causes them, they may be volatile substances sublimating, and they are unique to Mercury simply due to the proximity of Mercury to the Sun. They seem to be an active geological process, apparently some of the youngest features on the planet, and they are certainly not the result of meteor impacts. There is much more going on Mercury's surface. Ancient dried up lava flows, evidence of volcanic activity, craters from massive asteroid strikes that warmed its surface, and surprisingly, the thin scarps that were evidence of its gradual cooling. These scarps show that Mercury is contracting, and from MESSENGER's data, Mercury has contracted by over 14 kilometers in diameter since its formation, a lot more than was expected. All these findings have thrilled scientists. Yet even though we would barely know anything about Mercury were it not for MESSENGER, somehow this mission isn't that well known among the general public. Perhaps ESA's Bepi Colombo mission, already on its way to Mercury right now, will better capture the public's imagination when it arrives in 2025. Let's go back to when the planet was warmer. So warm in fact, that it becomes necessary to ask an important question. What happens when a planet melts? For Mercury, this is no idle question. At the risk of it being understated, Mercury is a very hot planet. With daytime temperatures reaching an incredible 430 degrees Celsius, the temperature of some wood-burning fires, the rocks and dust on Mercury's surface bake beneath a blistering heat that pushes them towards their limits. It's not the hottest planet in the solar system. That honor goes to Venus, thanks to its thick atmosphere, but it's certainly up there. The Mercury we know today has actually cooled considerably over the years. There is ice at its polar caps, and we discussed the signs on its surface that show it has contracted over time as its interior became colder. So, what was it like back then? When rock is sufficiently heated, its solid structure breaks down and it turns into the gloopy, viscous liquid known as magma, with a viscosity, or runniness, 10,000 or 100,000 more viscous than water. For a point of reference, this is similar viscosity to tomato ketchup, although I would not recommend putting this on your food. Depending on the rock type, magma forms at temperatures of at least 600 degrees Celsius, but potentially as high as 1,300 degrees Celsius. So, for Mercury to have begun to melt, we know that it must have reached at least these temperatures. In spite of being much less runny than water, lava can still travel for great distances before stopping. This is because once the surface of lava hardens, it forms an insulating layer that keeps the rest of the lava within protected so it can flow freely. How do we know this happened on Mercury? The clues can be found in craters like Radit-Tladi. Scientists estimate that Radit-Tladi is a relatively young crater, likely under 1 billion years old, with well-preserved walls and a floor relatively clear of other later impacts. It's large, over 25 kilometers in diameter. Notice how rough the hills are around the crater, and yet inside is a smooth plain. This is no coincidence. Originally, the terrain inside Radit-Tladi was likely about as rugged as the hills around it. So why is it so smooth now? The answer is lava. When lava is left on its own, it will try to form the flattest surface possible, just like water does if you put it in a bowl, as it is dragged down under the effects of gravity. The same happened here. An asteroid crashed into the planet's surface, and the crater quickly filled with lava. Once the lava cooled, it formed the smooth plain you see here. But where did this lava come from? There are two theories. The first is that the impact of the meteor triggered a creeping volcanic eruption, as magma from beneath the surface rose up through the cracks to fill the basin. The second explanation is that the surface within the crater got so hot due to the impact of the meteor that it pushed the already hot rock crust over the tipping point into melting. This kind of lava is known as impact melt. The true explanation is likely a combination of both. Now that we know that smoothness is a sign of lava flow, we suddenly realize that there are numerous other craters on Mercury that similarly must have been filled with lava. Just look at Rustaveli, where crags of mountain can be seen poking up through the smooth lava layer. Or Copland, Polygnotus, or Rachmaninov. Rachmaninov is particularly interesting, as here you can see the strong indicators of lava bubbling up through from beneath the surface to the center of the crater. Take a look at the strange, crinkled cracks forming a rough circle inside the central crater. Such craters are a signal that a slower outpouring of magma pushed up from beneath the surface, breaking the plane, then pushing up, and then cooling again under the effects of Mercury's fluctuating temperature. Here, and in many of these impact craters, the collisions from space triggered deep volcanic activity from within Mercury's shell. But lava didn't just flow within the craters. Let's look at the valley known as Angkor Vallis. Here you can see clear signs of smooth lava flow, but this time moving like a river. The lava traveled from high to low ground until it eventually poured into the basin next to it. Flows like these ended up filling massive seas, taking up vast swaths of the planet and turning them the more orangey color we see today. Scientists have begun to recognize this telltale orange color as a sure sign of volcanic activity, and from it, a more detailed picture has begun to emerge of conditions on early Mercury that make it even less hospitable. Areas like this one to the northeast of Rachmaninov are likely formed by volcanic activity. When Messenger flew over this area in 2015, it took detailed photos of it, and found the surface to be covered in a fine dust. Upon review, it was obvious what this dust was: volcanic ash that must have fired out of vents and covered the terrain around it. NASA scientists likened it to snow, fiery, hot, angry snow. So it wasn't just lava flowing beneath your feet that you'd have to contend with on Mercury, but burning ash falling from the sky. And that was just the calmer volcanoes. The final indicator of volcanic activity on Mercury hints at eruptions so destructive that whole chunks were scooped out of the planet. Take a look at this crater Navoi. This is no impact crater. When a crater is formed onto a hard surface, one that's not sufficiently hot to melt into lava, a central peak is usually formed. This is because when the crater walls suddenly find themselves exposed, gravity suddenly exerts itself on all that loose particulate, which rushes down the walls of the newly scooped out basin towards the center. Once there, having built up momentum, it comes crashing into all the rocks and landslide that is sliding down from the other side of the crater. The two sides meet, and all that momentum and energy forces them to keep moving in the only direction they can, up. You see the same effect more clearly when you throw a large rock into water. The water of the newly formed basin rushes in to fill the gap, but then crashes into water from the other side, and all of it shoots upward in a powerful secondary splash. But unlike water, the sand and loose rock of a crater does not level out, but forms a central peak. Depending on what angle the meteor impacted, this peak is either perfectly rounded or possibly teardrop shaped. However, the raised central formation of Navoi is neither of these things. As scientists looked at this, they came to the conclusion left, that this crater was not formed by an impact at all. Instead, it had been carved out through the force of an erupting volcano. At 66 kilometers in diameter, the amount of force exploding upwards that would have been necessary to carve out this crater and scatter its remnants for kilometers all around must have been truly massive. So, there you have it. Meteors raining from the sky, tipping the rocks they landed on over the melting point. Volcanoes bursting forth, either filling the landscape slowly with bubbling magma in lakes and fiery rivers, or choking the air with burning ash. Not that there was any air to begin with, beyond the thick toxic gases emitted with the eruptions. And even the ground you could stand on might at any moment explode under your feet. This is what it was like when a planet was melting. Mercury is quiet now. As near as we can tell, there are no longer any active volcanoes on the planet. Although the sun still bakes down on it, the unbridled fury that raged beneath its surface is now calm and soothed. Yet, for all those who know how to look, the evidence of what once was is still there, locked in the geological record. It's the scars that tell the story of a violent past. When something is as incredibly difficult to get to as Mercury, it is extremely tricky to study. Which is one of the reasons why in all of human history there have only ever been 2 missions to Mercury, with just one more on the way. Mariner 10 in 1974, Messenger in 2011, and Bepi Colombo due to arrive in 2025. Of these prior 2 missions, only Messenger went into orbit around Mercury, and so it is the only mission to ever give us close-up shots of Mercury's surface. And crazily enough, some of the formations we've seen on the surface are still unsolved mysteries even more than a decade on, while other formations give us hints at the raw primal power of the early solar system. So let's finish by taking a look at some of those mysteries and formations and see what answers we can find. When you look at the surface of Mercury, there are a few features that immediately jump out at you. First, its color. Mercury's color is not actually monochrome and is smattered with speckled greys, creams and beiges with lighter sections and lines. These darker sections are believed to indicate high levels of graphite, the same material used in pencils, and the lighter sections, well, we'll get onto them later. Beyond that, you most likely noticed the craters. Much like the Moon, Mercury is covered with craters, as ancient pieces of space debris crash down on the unprotected planet with a roughly even distribution. These offer fascinating insights into the planet's violent history. You can get a sense for how old a crater likely is by how sharp its crater rims are. Sharp and crisp rims are likely a lot more recent than the older, rougher rims that have had more time to erode down due to the natural processes happening on the planet. Sometimes asteroids strike within the same place as older collisions, creating overlapping craters of differing ages, such as the craters here. But it is in the difference between these older and younger craters that we get our first fascinating clue about the surface of Mercury. It is an active, flowing place. Although there is no real atmosphere to produce the weathering we would imagine, evidently things on the planet's surface do not remain static on an astronomical timescale. As previously mentioned, Mercury is cooling, and as it does so, its surface bunches together in kilometer-long scarps. But Mercury's surface is not just crumpling, it is also smoothing out. In this crater, there is evidence of slumping having taken place. While about 90 degrees of the crater wall has retained its shape, the remaining 270 degrees has slipped further into the crater bottom, breaking away from the rest of the rim under the force of its own weight. Scientists are not entirely sure why this happened to only some of the crater and not all of it. Is the soil particularly hard in the bottom right corner? Was it something to do with the angle the impact is struck at? We don't really know, and that's one of the things that is so intriguing about Mercury. There is still so much more to discover. Here's another interesting phenomenon. In my videos about the Moon, I mentioned crater rays, or ray systems. These spidery lines that radiate out from certain craters are a prominent part of Mercury's surface as well, with some stretching over 400 kilometers across. Their lighter color is a sign that the material kicked up from under Mercury's surface is less graphite-rich, or at least is a different chemical composition to the sun-exposed surface. But did you know that for a while, scientists could not account for how these spidery limes were formed? When they tested different weights, consistencies of terrain, and speeds of impact, they were unable to recreate these patterns in lab conditions. Whatever they tried, the material they kicked up would always return back down in a consistent circle, not thin spider web lines. Scientists racked their brains for years, but now it seems that this mystery has been solved. In 2018, a scientist called Tapan Sabharwala was scouring the internet and discovered that a group of students had managed to recreate the spidery line pattern of crater rays. Sabharwala was excited but also confused. Why were these students able to manage what other scientists had not? Interestingly, he realized that this was an example of scientists being too neat. Before performing their tests in lab conditions, Sabharwala and other researchers had always prepped the experiment by smoothing out the sand their test asteroid was impacting into. The students had not done this step, leaving the test surface rough. This made sense in hindsight, as it more closely mimics the rough terrain on the surface of an alien planet. And as it turns out, this was the entire key to know how these rays were formed. Crater rays do not care about the speed of the impact, the angle, or the composition of the crust. They only care about the surface shape and how rough it is. Knowing that this is how these lines are formed, it really opens your eyes to the scope of some of the impacts that have struck Mercury in its past. Remember I mentioned how some of these ray systems stretch over 400 kilometers? That was just the smaller ones. Look at the ray system originating from the crater known as Hokusai. These rays must have been created from an incredible impact, as their lines stretch almost entirely around Mercury's surface, which, by the way, has a circumference of 15,000 kilometers. And although not quite as large, the ray system of the crater Debussy covers over 1,000 kilometers. While the Moon also has ray systems, they are usually smaller than these. In fact, one of the main visual distinguishing aspects of Mercury are these giant ray systems. These show us that one of the formative processes that explain Mercury's unique surface is incredibly powerful bombardments. Seeing as the Sun is so nearby, objects caught in this intense gravitational pull would crash into Mercury with far more force than Mercury could produce with its own gravity. Mercury's gravitational pull is so weak compared to the Sun that Mercury cannot normally capture objects as moons. They get pulled past instead. This is one of the reasons why visiting Mercury is so difficult for spacecraft. But that's not to say that Mercury can't stop such an object reaching the Sun, it just has to body block it. Yet, this explanation cannot explain this last formation. Take a look at one of the most fascinating craters on Mercury, Apollodorus, and its surrounding Pantheon Fossae. At first glance, you might think there is nothing unusual about the crater Apollodorus. Yes, those fractures running out from the center are a little unusual. There are a few features that are odd here. To begin with, the fractures and the surrounding radial fractures bear a strange resemblance to fractured glass. Glass fractures in this way due to its hard but brittle qualities. As you have seen, most other craters we have seen on Mercury do not follow this pattern. The crust of Mercury does not tend to fracture, but instead sprays in ray systems or just leaves perfectly round craters. This is in keeping with a looser material makeup. Sand does not fracture when hit. We do not see this fracturing anywhere else on the planet either, so something unusual is clearly happening here. Was the surface of Mercury particularly cold and hard when this impact occurred, thus making it more brittle? Mercury's nights can get as cold as -180 degrees Celsius. But if that was so, why has this not happened in other places? About half the impact should be hitting Mercury's night side at least. When we take a closer look at Apollodorus, the crater you might assume is the cause of the fractures, we notice something even stranger. Apollodorus is not quite the epicenter. While it's pretty close, it doesn't actually line up. This might suggest that Apollodorus and the spidery fractures of the Pantheon Fossae are actually unrelated. Whatever caused this phenomenon may have happened only to be later hit by an asteroid near to, but not on, its epicenter. But if that's so, what caused Pantheon Fossae? The intriguing thing is that we don't know. Evidently, something created this fractured glass shape, but left no crater. Might that imply that this is the result of not something hitting it from above, but pushing its way up from beneath? Perhaps this is the result of immense volcanic activity, suddenly pressing up and cracking the crust. That's just my guess. There are still many mysteries to be found out on Mercury's surface, and many other fascinating insights to be gleaned as science advances. When ESA's Bepi Colombo arrives at Mercury in 2025, it will begin another extensive study of the planet, and perhaps then we will have the answers. Bepi Colombo will uncover the characteristics of Mercury's magnetosphere and exosphere, and will take a clearer look at its geology and composition. But until then, scientists will continue to pore over the data we have. For now, Mercury endures, baked in its solar furnace. It has survived there for millions of years, and will likely survive for millions of years, in spite of all that the Sun and the solar system have to throw at it. The hellish conditions of its environment make it challenging to get to, but there is no denying its resilience, shown in its charred, cratered beauty. Perhaps one day we will know all there is to know about the first of the solar system's planets, but that day is not yet. In spite of it being the most illuminated planet in the solar system, thanks to its location, there is still plenty of light to shed on Mercury. Thanks for watching. If you enjoyed this supercut, be sure to check out my others in this playlist here. A big thanks to my patrons and members. If you want to support the channel and have your name added to this list, check the links below. All the best, and see you next time.